Welcome to today's lecture entitled Flow Force Compensation and Spool Design. This is continuation of the lectures on electrohydraulic valves. I have put this into a special topics, miscellaneous topics, because this is some detailed idea about how to design a spool and how to compensate the flow force. Now, it is already established that steady state flow force has substantial contribution towards the stroking force. If we look into this figure, which you have seen in earlier lecture, that how the flow force is working on the spool. If we look into the spool, then so let us consider the flow is coming like this and it is going out like this. This is full rectangular port. This means that there is a groove here, and so if we consider the length of this orifice will be pi into this diameter, and width is the opening, which is x v. Now, for this configuration, we know this flow will neither touch this wall nor touch this land with some sufficient velocity, or in other words, at very low speed and some valve configuration it may touch this land or this wall. Otherwise, it will make an angle to this path, which is theta, and it is possible to predict this angle theoretically. Now, what is happening if we consider this spool? On that spool there is a force on this wall. This is the pressure force. Similarly, the same pressure force is in the opposite direction, in opposite face of another land. Then we should consider, then these two will be balanced. But if we consider this jet, then definitely there is a force. There is a force, because this oil is moving in this directions. If we follow the Newton's laws, then there will be force, and that force, if we resolve, this will have one in the lateral direction and another in the axial directions of this spool. Now, this force is called flow force. This flow force, even at the steady state conditions, if we look into this flow force, direction of this force acting on the spool is in this direction. That means, it is trying to close this path. Okay. Now, while we are estimating what is the force required to move this spool, then this flow force having a contribution, substantial contribution towards this total force. Apart from the other this force, when this spool is accelerating, we have to consider the mass of that, and if there is pressure imbalance anywhere, we have to consider that force also. So, total force is calculated in that way, but this force may be 30%, 50% of the total force. So, if we can reduce this force, definitely then control of this spool, because we have to drive this spool with some force, with some actuator. That actuator, if it is a hydraulic actuator, then there is less problem, but if it is solenoid drive, that means electrical drive, in that case to generate that force and control of that is difficult. So, better to reduce this force if we cannot eliminate. Now, this force this F1, the which is the steady state flow force, can be estimated like this, which we have shown earlier. Now, C D is the coefficient of discharge, C V is the velocity coefficient, A 0 is the orifice area, P 1 and P 2 is the pressure difference, and cos theta is the jet angle. That derivation is shown earlier. Now, this is important. I have already discussed this force will try to close the port. Now, let us consider a large valve. Okay. Again, it is four-way valve of spool diameter 25 millimeter. Once we say that spool diameter, this means this larger diameter, other is called stem. So, spool diameter means this is 25 millimeter. Stroke of 0.5 millimeter, that is the XB is 0.5 millimeter at pressure 7 megapascals. Then the force, the stroking force may be estimated as large as 80 Newton. This considering the acceleration of this spool also. If this spool has constant velocity, then there is no force, but when this is accelerating or decelerating, there will be additional force. So, summing up all such force, it is 80 Newton. So, with hydromechanical devices for stroking, handling such a force is not a problem. However, for electromechanical devices, it is nearly the upper limit of available generated force. Now, upper limit, this term although we have used, we can go for bigger solenoid, but looking into the size of the spool, normally the size of the drive solenoid should not be very big than the valve. So, in that case, whatever the solenoid size we can provide with these dimensions, we can see that this is almost the 80 Newton is almost the upper limit of the available generated force. In designing direct drive valves, because this valve may be this is the main spool, may be direct drive, which are gaining popular for more reliability in some areas like an aircraft applicable, it becomes crucial. This means that sometimes why sometimes in many operations, instead of pilot operated valve, the direct drive valve is preferred, the response is better. Now, pilot operated valve, as I have mentioned, that is called two stage. So, that is like it is like that when there will be some signal to move, that the spool will move the pilot stage. Now, through this pilot stage, this may look identical like a spool valve, but small spool. Then there will be a small force which will be diverted to this either this end or in the opposite end, which will generate this force, maybe say 18 Newton or that level to move that spool. So, that can be done, but response of such valve is much less. So, in many cases direct drive valve is required. Then for direct drive valve, we cannot use this, or even if you use that hydraulic, again some controllability problem will be there. So, in that case, if we would like to use the solenoid, better to reduce this force. This is the only area which we can reduce, that I have mentioned. Therefore, reaction of flow force is desired both for direct drive single stage, and also if in case of pilot operated, it is better if you can reduce this force. Now, proposed methods of steady state flow force compensation by modifying the spool design are generally employed. Okay. So, one is that we can move this design of such spool as well as maybe the sleeve, because this is not the direct body of the valve, usually this will be a sleeve. So, we can modify design to reduce such force. It increases the manufacturing cost definitely. If we want to, this is very simple, thus just a step down. Instead of that, if we would like to modify this profile, naturally the manufacturing cost will be more and even increase nonlinearity in controlling the force. Sometimes due to this curve or maybe some profile which I will show, nonlinearity will increase, but still reduction of this force is required. Now, so there are one can think of many methods, but all may not be acceptable due to the nonlinearity in control or too much increase in the cost of manufacturing, but there are some popular design which are accepted for flow force compensation. Now, one is that jet angle modification. Say for example, if we can make this angle 90 degree, that means straight directly it is going in the upward directions, say, then definitely there will be no component in this directions, and one can see this. You may ask that, but F 2 will be there, F 2 will be large, but F 2 is uniformly distributed over the circumference. If not uniformly distributed, it might be discrete, but at a certain angle equal amount of force. So, that will cancel each other. So, we can make this theta 90 degree to make this flow force 0, but it is not possible by providing this groove design. One way of making the jet angle 90 degree, not exactly 90 degree, but close to that, is that instead of making the rectangular groove for port in the valve sleeve, say this is the rectangular port, very common for that rectangular port, because this machining may not be that difficult. So, flow can go like this. So, this is the 90 degree. Sorry, this is the jet angle. So, for full rectangular port, we cannot reduce this theta to 90 degree, reduce, or maybe we would say that to make it 90 degree, it is not possible. Then what we can do, we can provide the rectangular hole at different positions, maybe 4 at a 90 degree, maybe 6 at 60 degree or more, but making such rectangular hole on this sleeve is difficult. Say one is that electrohydraulic that is non-conventional machining, electro discharge machining or something can be provided, but for mass scale obviously it can be done with the use of broaching. How it is done? That first we make an hole, circular hole by drilling. Say if it is a 90 degree, just 2 cross hole we can provide there, and then using a broaching tool we can make this square hole. But it is seen that if we make such square hole, then this flow jet angle may be 90 degree, very close to that. Okay. So, and if we can make it is 90 degree, because cos theta will be 0 in that case, and there will be no component in the in this axial directions. Okay. It is to be noted that the rectangular holes are better, but the circular holes in compensation of linearity also serve the purpose. This means that, as I told, we make a circular hole, then we broach it. Instead of that, we can have a circular hole there also, that will serve the purpose. That means that will compensate the force. However, there will be more nonlinearity due to that. Now, larger spool end diameter is also another solutions. What it is? We can make this land diameter is more, also the stem diameter as you see here is more than what is at the middle. Now, in that case what happens, that due to we have to make this groove depth and here also depth in such a way, we can see this angle is more than its normal angle, it is close to 90 degree, and the flow force is reduced, not fully compensated, but it is reduced. But this is to increase the flow rate, and thus the pressure drop in the opposite side of the flow force to have more force opposing the flow force. This means that usually larger diameter means there is a orifice opening, because this length is more. So, for a same stroke the orifice size will be more, there will be more flow, and the pressure drop will be more. In that case the pressure is compensated. Okay. It reduces the flow force to some extent. However, this is effective only for large flow valves. That means, if we use such valve, say for example, as I told, the 25 millimeter diameter, that may be around 25 liter per minute flow rate, very high flow rate. For that valve, okay, it is okay, 25 millimeter is a large dimension if we think of this valve design, spool design, and therefore, it is possible to compensate to some extent this force. Moreover, such compensation named as pressure drop compensation, it is, we call it large spool and diameter from the end diameters. This is from the spool configuration, but actual the mechanism is that pressure drop compensation is not effective for partial orifice port valve. So, that means, if we use that rectangular ports, a few rectangular ports instead of full port, it will not work. Another method is that recirculation land for compensation. Now, in that case, let us look in this valve what is happening. The spool end lands are made of specific profile. This profile is made like this. Okay. Now, also the sleeve groove is made like this, but still if you look into this, the port is the orifice is rectangular, full rectangular, because orifice area is calculated this stroke length into pi into this diameter. So, this is rectangular, but instead of rectangular groove, this is somewhat spherical groove inside. Now, for that what we see, that whatever flow is coming, due to this profile it is recirculating. Thus, once it starts recirculating, then this although here is the jet angle, but due to this flow there is another force. So, that force counteract to each other, and in that case the total flow forces reduces. But if we look into this, what this is a obviously special design, not as simple as this. For that what will be had, what we will have, such lands recirculate the flows before their way to final return path from the valve that I have discussed. As a result, an opposing force to the flow is generated. Now, but this design again usually made for very large flow, because for small spool giving such profile is difficult. Also nonlinearity arises, and apart from the cost giving a special profile. Now, another possibility is that we can generate some negative force by designing the port accordingly. Now, for that what we find, negative force port is designed providing specific spool end profiles and length dimensions and the grooves in the sleeve. If we look into this in comparison to the earlier one, there it was a spherical, instead of that it is stiff and an inclined surface. Due to that, as you look into this, instead of flow moving in these directions, here it is of course moving in these directions. On the other hand, it is moving in the from here to here, it is moving in these directions, and there is a recirculating. Due to that, the force is negative. It can be calculated, design can be made such that flow force is negative. That means, this will try to open the valve, and ultimately to move a spool in this direction, total force will be less. Now, it gives better compensation in the expense of manufacturing cost. If we can use this type of port, then it is better, but manufacturing cost is high. Now, these are the few methods which I have shown. For specific amount of compensation, care must be taken in design. Say, if we this means that we can optimize something. It is not always expected that the flow force will be 0. We can have some flow force, and designing the drive, that means designing the solenoid or any other drive, and keeping the compensation force to a limit, we can have some optimum design. Now, using such methods, what type of compensation may be available? This is described here. Say, for example, that this is uncompensated. That means, if we take this type of valve directly, then what we find, that this flow force will increase with this valve stroke length. Okay. This is almost linear for this type of port. Now, if it is compensated, a good compensated valve is something like this. Now, this, say for example, negative port, sometime it may become overcompensated. Now, overcompensated is having a difficulties, because this, due to this flow force, in that case it is trying to open. What we are giving? We are giving the force in the direction of the stroke, but if flow force overcompensated means flow force is trying to open the valve. That means, if we keep the valve without any force, due to the flow force, if there is leakage, that will try to move. So, controlling of overcompensated valve is difficult. Nonlinearity and the stability are two major criteria. Now, nonlinearity we understand, say for example, this type of, when it will come, that what we will find, the force not always a constant, it is varying, again not linearly varying. Then controlling of such force will be difficult. I mean, it is nonlinear control we have to introduce. And stability is another point. Stability means that when we are moving the spool, it has dynamics. Then we have to stop the spool at a particular position, because we one, a definite movement of the spool. But what happens at that condition, starting at the starting point particularly and the stopping point, it will try to vibrate. So, we have to consider about that part also. It might be sometimes that flow force is better from the control point of view of the stability. Okay. Now, apart from this the linear force, there is also lateral force on spool valve. Now, as I have described, if I consider this force jet force, then this is having two components F1 and F2. F1 is the flow force which we cannot balance, we have to control, we have to add, we have to control this force by the drive. But there is also the lateral force F2, but for the full rectangular port or for the uniformly distributed small rectangular ports, or may not be rectangular also, uniformly distributed. If we look into this F2, ideally they are equal and opposite. So, they are cancelling each other. So, there is no chance that there will be lateral force, but there may be lateral force due to several reasons. One is that, say for example, instead of this full rectangular port, we have used say small holes, discrete rectangular holes. They are uniformly distributed, let us consider at 90 degree, but again due to the manufacturing error, there might have, they are not exactly opposite to each other. Two are opposite, but they are, say for example, center through these holes, through holes is not coinciding with the center of the slips. So, in that case there will be an imbalance. This is from that point of view. Again, if we consider this cylinder, this cylindrical surface, that cylindrical surface may have several defects. One is that they are not perfect, the surface is not parallel to the axis, some taper is there, or the center of this and center of the spool is shifted, sleeve, center of the sleeve and center of the spool is shifted. So, in that case what will happen, there will be imbalance in this force, this F2 will not be properly balanced. In that case, the spool will try to move towards one side and it will touch the sleeve, and touching the sleeve means we need more force to control. So, lateral force we must consider while we are designing the such lateral force. However, this is we cannot estimate such lateral force, because these are due to the manufacturing defect, and estimating such manufacturing defects and calculation of lateral force is very difficult. Only experimentally we can find out, and we can provide some methods so that this force is also reduced. Now, lateral components of the steady state flow forces may not be evenly distributed around the periphery of the port openings, are not evenly distributed. This is due to this reason which I have already explained. Secondly, the leakage past the spool land causes lateral force. Say suppose this is slightly moved in this direction, then leakage flow started, and that flow is having some lateral force that will further push this spool in one direction. Thirdly, and most crucial one is that due to taper land and or sleeve bore may be also tapered, non-parallel cylindrical surface with central axis etc., and these are due to the machining error, a lateral force is generated. Now, how it is generated we will see in the next slide. Now, this is the ideal one which I have shown. Now, let us consider this land is like this instead of the cylindrical perfect cylindrical is taper. Of course, this is an enlarged view, it will never be like this, but there may have slight taper, even that will cause substantial lateral force. Now, such lateral forces are normally not balanced and push the spool to slip. This is obvious. Now, due to tapered duct, what we will have? Say this, first of all, this spool axis is not matching with the bore axis. There might have some, suppose let us consider a small amount of lateral force generated due to some reason. After that, what we will find that if we imagine a ring over the periphery, then here might be the smallest distance, here may be the largest distance. So, in that case, this path of different area, or we say varying area over the periphery. In that case, if we look into that, in case of parallel duct, if this duct is parallel, then P1 is P2 is like that, pressure variation will be like that. If it is a tapered duct, then pressure variation will be like this, and that definitely you can see that instead of parallel duct, this will generate a force. You see this due to this non-linearity. And the other side, if you look into other side, then this is also some parabolic shape, but we can see that there is a difference. Difference is due to that opening area. This means that due to this there will be definitely a lateral force in these directions. Okay. But if it is perfectly parallel, due to this flow there will be no lateral force. This also not only for spool, this happens any piston cylinder. When the spool or piston is moved, additional force is required to overcome internal friction force caused by the lateral push. That is obvious. Now, how to compensate this? What we can do? We can provide a groove here. Now, providing this groove, what happens? Let us see. Making a groove over the spool land, the piston, the lateral push force can be reduced to some extent. How? If we now look into the pressure distribution due to this groove, this distribution will be something like this. Okay. Due to this, what is happening? Whatever the pressure here, this is connected to other side. Say if there is no such groove, but keep in mind this passage what we are looking into much smaller than what we are looking into. This is real sense, that will be capillary passage, because these are the sleeve and the spool, they are very close fit, and the difference in diameter may be only 20-25 microns. Okay. However, if we make a groove like this groove is having a substantial depth, maybe 0.5 millimeter or something like that. This means that this path is directly connected. So, throughout this groove the pressure will be same, and due to that this pressure curve will be like this. So, without groove this is the curve pressure distribution, and with groove this is the pressure distribution curve. If we look into the other side of this spool, what is there? This side also difference in this pressure distributions. Now, here much I mean larger difference as this deviation was more, in that case a little less. But ultimately what is happening, if we now estimate at least at that portion the force is very less, that means totally the effect is that lateral force is reduced. So, this is the method of compensating the lateral force. That is why you will, if you will observe a spool, you will find on the spool there are grooves. This providing such grooves has other problem or merits, demerits are there. Say within this groove sometimes the dart particles are accumulated, that gives a problems later. The resultant push force affecting the spool, effect of compensatory, pressure equalizing and centering groove etc. are these grooves. These grooves are called pressure equalizing groove, sometime that pressure compensation groove etc. Now, in spool valve design, 1, widths of the porting lands must match with the corresponding port widths in the sleeves. Now, importantly, say for example, it is a critical center valve. In that case, this width must be equal to width of this land. So, and critical center valve is preferred due to the quick response time over the null point. However, maintaining such dimension is always difficult, because not only that, but also we have to maintain the distance between, say for example, from this point on the sleeve, from this point to this point, what is the distance, same distance may have to measure, or the proportional distance has to be measured from one edge of the land, the same similar edge in the other side. So, maintaining such dimension is difficult. However, we have to maintain that for better performance. Distances between lands must match with the corresponding dimensions between groove in the sleeve, and finally, closed tolerances must be held between the spool length diameter and corresponding sleeve bore diameter, and on squareness in the length and the port groove edge. Now, this is another important factor, is that this edges, say from the movement point of view, we may think of that we can provide a chamfer here, we can provide a chamfer here, but if we provide a chamfer there, immediately valve performance drastically falls. This is because drastically reduces. This is because of the reason that in that case, at the time of opening, this jet angle will be different and response will be much poorer than if we can maintain the sharp edge. Maintaining the sharp edge at the opening, there will be the turbulent flow, but that turbulent flow is preferred from the response point of view. If however, if these edges are very sharp, in that case there is a problem that due to this lateral force it may get stuck there. So, to avoid that, there is a small the breaking of such edge is done. That means, you may find if it is measured, a small not chamfer, you can say round up is done at these corners. Okay. However, it is better to keep these edges as sharp as possible. A tolerance of, as you can see, 0.0025 millimeter. Look at the tolerance. This 0.25 millimeter is typical for a high performance servo valve. You see this, to get this tolerance, not only this dimension control, but also the surface finish is required. So, you can imagine how accurate machining is required. However, it may be plus minus not 75 millimeter in general cases, say a little lower performance, low performance valve or maybe general purpose valve, but these are for very accurate position control or velocity control. Valve coefficients such as flow, gain and pressure sensitivity at null point depend on these tolerances. Now, choice of ways. This is what is way. Say if I say that 4/3 DC valve, that means 4 port 3 position or 3 way valve. So, that is called way. Now, no 4 ports 3 position, that means 4 way 3 position valve. First one is the number of port or way and second one is the position, but here the way means that port or the how many directions the flow occurs. So, how to select, or I would say that where it should be 4 way or 3 way or 2 way, that is an important factor. We have to, according to requirements, we have to make a choice of that. Now, general choice is 4 way valve, because 4 way valve is in it is easy to think of the system as well as maybe from control law point of view. However, this with the number of ways the cost also increases. Now, in some specific applications 3 way valve is better. One actuator line, of course, with linear actuator only, is one example of 3 way valve application. Less number of tolerance is required in such applications. Say with the linear actuator and with 3 way valve, the system becomes simple, compact and relatively it is also controllable. So, where we are moving this actuator frequently in opposite directions, then 3 way valve is a good choice. Another factor is the number of lands in the spool with respect to the number of ports, that is ways in the sleeve and their locations. You see, this I will show that 4 way may have 3 lands, may have 4 lands or may have 2 lands also. So, it can be made like this, but they have own merits and demerits, which I shall discuss. Now, various configurations as shown are possible. First, let us consider the 2 land 4 way spool valve. This is 2 land, but there are 4 way. What are the 4 way? If you see that this is the supply flow, let us consider this is a critical center or even if you overlap valve, but still when it is in neutral positions, this it is totally closed, it cannot go in any directions, this flow. So, that means flow is being bypassed through the relief valve, maybe. Now, if we move in these directions, then oil will be supplied through this and this will go one end of the actuator, and from the other end this oil will return back to tank. If I move in the opposite directions, it will be vice versa. Okay. So, this is one configurations. Now, if we look into the other, this is 3 land 4 way spool valve. In that case, what is happening here, the oil is directly coming to inside the valve, inside this spool stem, and it can move in either direction. But if we consider this valve, so this, when we are moving in these directions, the oil is going like this and the return oil is going back through this path. Okay. And if I move in the opposite direction, this will be opposite. So, now there is a question that why we should go for this. We can make this is a very simple, but we will see that these two is having some differences also, merits and demerits. However, the another valve is that the tool and three-way valve, that is with the actuator, but before that we will also see another valve, that is, if we say this is again four-way, but we have four land. You can see apart from these two land, there are another two land through which the oil is going back. Okay. So, starting from this one, this is the two land, this is three land, this is four land, but all are four-way. So, which one we should choose and why? If we can do the same job with this valve, why we should go for four land or three land? Okay. Each of such spool sleeve arrangements has merits and demerits over the other. Now, if we look into that such merits and demerits, then first of all, if we consider two land valve, that is two land four-way, this is shorter in length, simpler in construction, statically unbalanced, as in two return lines resistances are not identical. For full port, the lands may lodge into the sleeve grooves. Say in this case, say for critical center, it might happen, you can see that this simply can go inside. Say this is a full rectangular port. Okay. Now, this sleeve height or width, whatever we call it, is exactly ideally is equal to the groove width. So, in that case, for full port, simply this can go inside, and also when it opens, we can see this unbalanced force. Now, remarks force imbalance tend to open the valve further in this case. So, stability even at null point is difficult. Now, if I consider the other one, that means which is having the three land, moderate in length, statically balanced. This is statically balanced. Say if we look into this, this will not try to move this or that way, because this path is closed and these are widely used. Now, if I consider the other one, that is the last one, that is the four land and four-way, then operationally same as two land valve with two additional end lands, preventing leakage and providing better support. So, if we had to compare, then we can compare this one with this. In that case also this is open, directly flow is coming to the spool. So, this unbalance will be there, but as there is a land support, there is no chance it will go into the groove, and also there will be the leakage will be less. In that case, this directly this is open to the I mean outside, and the leakage has to depend only on this seal. In that case, this path and then sealing. Okay. So, operationally these two are same, but this has much better performance, whereas this is slightly different configurations. However, from close observations it reveals that all such four-way valves shown in the illustrations are required same number of tolerances. That means tolerances means say this width, so maintaining such width and this length, here this length, here in relation to this length, all has to relate with close tolerances. So, that means if we think in terms of tolerances, it will be same for both, but obviously this will be more expensive than this one. Now, next step is the choice of the type of valve center. That means valve center means that is a closed center, open center or critical center. For linear flow gain with optimum or zero dead band, a critical center valve is the obvious choice. Open center valves are preferred for high temperature applications allowing flow at neutral zone. You see, if we prefer that there is a high temperature and that temperature to be cooled, in that case it is better to keep this center open at null positions. But the problem is that for quick action, that means if we give a stroke, the response will be delayed due to that, and in many cases it is not tolerable, it is not acceptable. But high flow gain at null zone deteriorates the response at that zone, which I have mentioned just now. The power loss at null due to the central flow is another disadvantage. The closed center valve has dead band, no flow gain at null, resulting in loss of control loop at null. The valve area gradient is the principal parameter in the null flow gain, one of the major criteria in valve selection. Now, I have given some also the practical data. It is 6.5 10 to the power minus 6 meter cube per second, that is it is 6.5 cc, and 3.5 into 10 to the power minus 2, that is 3.5 liter perhaps per second. Flow gain per millimeter of stroke is usual range. The spool diameter is selected accordingly. Okay. Electrohydraulic servo valve have stroke ranging from 0.12 to 0.25 millimeter. Just imagine how small it is, 0.25 millimeter, 1/4 of a millimeter. It may be very large stroke to have 45 liter per minute to 200 liter per minute. You just imagine the orifice size. It even if rectangular port, say diameter may be 10 to 25 millimeter and width 0.25, such a small hole, but flow is 45 to 200 liter per minute. Higher stroke range from 2.5 millimeter to 4 millimeter for large flow range amounting 400 liter per minute to 1000 liter per minute approximately in 3-stage valve is found. That is 3-stage valve. You see this pilot stage, then one main stage, that main stage is operating the another main stage. You can see this is for very high flow. Okay. Usually the maximum valve stroke is kept below 5% of the spool diameter for full periphery rectangular port to satisfy the flow saturations and valve strength conditions. This we should say that flow saturation means that I would say that with the stroke the flow is increasing, but we have to consider that too much nonlinearity should not be there. So, from that point of view the flow saturations and also the valve strength is the I would call the how much is the strength is required to move this spool perhaps. Due to several reasons, area gradient is given more attention than stroke length in valve design. Now, area gradient is the what is called the pi d is called area gradient, that is more important than the stroke length. That means that decides what should be the diameter of the spools. And we have followed this mainly I would say that hydraulic control system by Merit, that book we have followed, as well from to know we have for better knowledge you can follow also Martin and McLoy, particularly the orifice sizes, it is discussed in detail, and also in general terms if you have more idea about the valves and their applications etc., you can follow this Blackburn referred book also. However, the mostly I have consulted the Merit's book hydraulic control system. Thank you.